Welcome back, everybody, to this third part of section 9.7. We're going to talk about the law of sines. We're going to start with a couple of things that would really be fantastic if we knew. We know that we're able to solve any right triangle given just a couple of pieces of information, whether that's two sides or an angle and a side. We can figure out all 6 measures of a right triangle. Wouldn't it be amazing, just incredible, if we could do the same thing for any triangle? For acute triangles, for obtuse triangles, if we could figure out all 6 measurements of them with just a minimal amount of information. In fact, I think that is the first step to taking over the world. So this is my plan. If we can learn to solve all triangles, I'm not sure what the second step's going to be, but I'm pretty sure the third step will be rule the world. In any case, it would be fantastic if we had the ability to solve all triangles. The second thing we need to start out with here is remembering congruent triangles, our favorite subject of all time. Remember that by CP/CTC, if we have 2 triangles that are congruent, we know that all 6 of their measures are the same. So we're going to think of this in a slightly new way. If I can tell that 2 triangles are congruent, essentially they're the same triangle. And that means there's only one triangle in the entire universe that has these 6 measures. Now remember, we used various things to prove that triangles are congruent: angle, side, angle, 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 side, side, angle, side, and side, side, side. So we know that if we have 2 triangles where we have 2 congruent pairs of angles and the included side are congruent, then all 6 measures of those triangles are congruent, which means essentially that those are the same triangle. And there's only one triangle that's going to have all 6 of those measurements. That was the game of finding congruent triangles. So wouldn't it be incredible? Wouldn't it be wonderful if, since we know that if we have this information about triangles, we know there's only one triangle that will fit that. So maybe if we knew ASA or we knew AAS about any triangle, we could figure out all of its measurements. So if we have 2 triangles and we happen to know that they both contain angle A that measures the same, they also contain angle B that measures the same, and they both have an included side of length C, we know that these triangles must be congruent. So they must really be the same triangle. So what we're really hoping for here is just looking at this first triangle, knowing an angle, a side, and an angle should be enough for us to figure out the entire triangle. Because that's how we determine triangle congruence. That's how we determine whether or not 2 triangles are in fact the same thing. And there is a way to do it. I've split up ASA and AAS from SAS and SSS because there are 2 different rules that apply here. The law of sines, which we're talking about today, has to do with a case where we're looking at a triangle and we know either of these 2 scenarios. So we know an angle, a side, and an angle, or an angle, and then a non-included side. The next video, we're going to take a look at. This gives us a method to find all of the measures of a triangle if we happen to know a side, an angle, and another side, or if we happen to know all 3 sides. So let's see how this works for the law of sines. You'll notice that the cases that work with the law of sines are cases where we know 2 angle measures and just 1 side measure. And you'll see why this makes sense in just a second, but when we know more angles than we do sides, we can apply the law of sines. When we know more sides than we know angles, we can apply the law of cosines. Let's have a look at exactly what this looks like. So here's how the law of sines appears in your definition in your book. I figured I might as well stick something from the book in so you didn't have to look at my scribbling all the time. If we happen to know ASA or AAS, we can apply these formulas, which are really the same formula, and find all of the sides or angles of a triangle. So on our good friend triangle ABC, if I happen to know angle A, angle B, and the length of side C, I should be able to figure out the rest of the triangle. At least this is what triangle congruence tells us. I've got ASA, I must have one triangle, there's got to be some way to figure out all of the measures of this triangle. So let's see what this actually looks like. So knowing the measure of angle A, the measure of angle B, and the measure of side C fits with what the theorem says. Let's just try plugging in these values here and seeing what we get for the things that we don't know. And then we'll think a little bit more about why this works the way it does. So that's everything we know from what we originally got from this problem. But we actually know a little bit more than that. We can immediately find the measure of angle C. Just by the triangle sum theorem, we can solve for C as 98 degrees. Great, so we can change that directly in the equation that we have. So the only thing that we have left to solve for are the lengths of A and B. Well, all we have here is a proportion, so this isn't too hard a problem. Let's set up this proportion, since we know this is true by the greatest thing in the world, the transitive property. And we can just calculate the sine of 72, we can calculate the sine of 98, and we can solve for A, just by cross-multiplying and then getting A by itself. So let's do that. That's just cross-multiplying. Now let's isolate A. Alright, so this expression should give us A. Let's pop it into the calculator and see what the heck we get. Since we've solved completely for A, all we need to do is enter exactly what we have in this expression into the calculator. 30 sine 72 over sine 98. That should work. I don't think we need any more parentheses here because we're just multiplying and dividing. Gives us 28.8 units. Let's say we're rounding to tenths for right now. Let's write that down. Well, it certainly doesn't seem like an unreasonable number. If C is 30 units, A could certainly be 28.8 units. Now we can do exactly the same thing to solve for B. Let's set up our proportion. Let's cross-multiply, go to our calculator and solve. That gives us about 5.3. So just like that, knowing two angles and an included side, we were able to solve directly for the two things that we didn't know, namely B and A. And lo and behold, we have solved for a non-right triangle, in this case an obtuse triangle. So the thing I want you to keep in mind here is that this law of sines applies when we know two angle measures and one side measure. When that's the case, and it fits ASA or AAS, we know we're going to be able to solve for the rest of the triangle using the law of sines. Just setting up the equation as it is here, or as it is here. These are of course both true, they're just reciprocals. Entering your information and solving. We'll come back with a few more examples about this after we discuss the law of cosines. Thanks for your time today, everybody.